So I think we can start for today's lab interactive session. So welcome to all the students. This is week 9th live interactive session on chemical engineering thermodynamics, and we are almost like 3 weeks away from the final examinations. So this might be the like 4 more interactive, like including today, 4 more interactive sessions will be happening for all the content that has been pending in chemical engineering thermodynamics NPTEL course. Okay, so this is week 9, and welcome to all the students. A very good afternoon to one and all on this NPTEL online certification course on chemical engineering thermodynamics. So quickly, this course, like, it's been offered by Professor Garge Das. She is a professor in the Department of Chemical Engineering at IIT Kharagpur. A little bit about myself is that I'm the teaching assistant for this course, and I've been taking all the live interactive sessions from week 1 to week 12. So I'm Raspi Shubham Ajikumar, and I'm PMR scholar in the Department of Chemical Engineering at IIT Madras. Okay, so we'll begin with the week 9. So we are almost going to get completed with the courses content of uh, the chemical engineering thermodynamics. So this is a 12-week course, and week 9 is already over. So we will interact with all the concepts and the content that has been covered during the week 9, and so we'll go through some of the numericals related to that of the content. Okay, so the week 9 outline is somewhat like this. So the first one it talks about is the non-ideal solutions, and the second one it talks about the deviation from the ideal direct solutions. So until now, what we have gone through is we have seen uh, the concepts related to the ideal gases, non-ideal gases, as well as the various non-ideal equation of states, which like we have seen and solved many of the numerical problems and the MCQs and many more things related to that. So like non-ideal equation of states, like simply known as EOS, non-ideal equations of state. We have gone through Van der Waals equation of states, Redlich-Kwong, Redlich-Kwong, and Pang-Robinson equation of states. So these are just to say that if in a real world problems, all the gases will not be ideal. None of the gases will be ideal actually. So we have to solve the problems, real world problems, using this non-ideal equation of states. So how to use the non-ideal equation of states, and how to like you use even that for your numericals if they have been asked in the final examinations, how to use that. We have already gone through all of them in the previous classes. So if you have not seen that lectures, the time sessions, please go through that. It will be very helpful for all the students to go just have a quick one view for that. Okay, so for this week, like in the week like in the week 7 or week 8, it started with the solutions. Apart from gases, there are another part which is called solution, that is liquid phase. So we started with solutions, which was we have seen what is ideal solutions, what is non-ideal solutions, and in this week we will cover mostly the content related to the non-ideal solutions and the deviation from the ideal dilute solutions. Okay. So the first thing which came into the mind in the last week was the isotopes. So we'll just go through some of the contents, then we'll start solving some of the numericals. So why I'm saying isotope, I am focusing more on the isotope is because this is the topic which has been covered in the week 8, but we have not put much more emphasis on understanding the concept what is an isotope. So like I said, an isotope is a thing or is a point at which the two substances or the two solutions, not the solutions, two things like the two components, component 1 and component 2, if I take it for example, benzene or water or chloroform water mixture, they starts burning at the same temperature. So what happens if they start burning at the same temperature? They will not be able to separate these two components with the help of the distillation column. So what we'll do there, so the close burning mixtures are known as the isotopes. So what to do is to separate this isotope, we use the different type of antennas and solvent in the distillation column, and then we'll be having a two distillation column instead of one distillation column in the like for the best distillation. So for separating an isotope require two distillation column. In first distillation column, either an antenna or a solvent will be used depending upon the minimum and the maximum boiling isotopes. And what is it, we will see later on. Then the second distillation column will be able to separate the antenna and solvent from the main component, the component of our choice. Okay, so this is how this works. So just it's like I said, so isotopes are the corresponding mixtures. So isotopes are close boiling mixtures, and there are two types of isotope. The first one is minimum boiling isotope, and the second one is maximum boiling isotope. So minimum boiling isotope means the solutions showing positive deviation from the ideal AD. Similarly, is known as medium boiling. And similarly, if you see the vice versa of that is the exhibits a negative deviation from ideality. So these two terms are vice versa to each other. So this is known as how to identify what is minimum and what is maximum. If our system shows a positive deviation from the ideality of the Raoult's law, it's known as minimum boiling isotope. If it shows a negative deviation from the Raoult's law or an ideality, it's known as a maximum boiling isotope. Now there is an effect of temperature and pressure on the isotopic compositions of the mixtures. How to identify that? So the effect of the I've written on content here, which is the effect of pressure on the isotopes. So it is just the composition, isotopic composition shifts continuously with the change of pressure or the temperature. So what happens is that if you change the temperature and pressure, the composition of the isotopic mixture changes according to that. So the effect of temperature and pressure is predominantly affecting the isotopic composition. So now how we will be able to separate, we will see in the further classes. Okay, so this is one thing which we have not covered in the last week. I've just shown you the plots like in a px1 and txy diagram, and it asked you guys to identify which is minimum boiling isotope, which is maximum boiling isotope. Okay, and we have seen some of the other plots. There are 5 different plots, and we have been asked to identify. So there were these plots. So if we have gone through the lecture notes, so there were these plots and somewhat similar to this guy. Okay, so we have to identify whether which one is like a minimum boiling isotope and maximum boiling isotope in the similar cases. Okay, now I'll just quickly write down some of the points which we have covered during the week. So we have gone through the fugacity activity and fugacity coefficient for the gases and the non-ideal gases, but are not seen it for the solutions. So fugacity of vapor phase for a mixture fugacity of vapor is given by yi phi I air equation. For an ideal gas, it will comprise up to fugacity of vapor is equal to yi into p for ideal gas. Okay. Now for pure species, we can write it up as fugacity of the vapor phase is equal to P into pi into vapor phase. For pure species, ideal gas, as an ideal gas, pure species, you can write Fi of vapor is equal to P. And for real gas, Fi of P has to be found out. Okay. So similarly, we have fugacity of liquids, right? So this is what I have mentioned is fugacity of gases, fugacity of the liquid or the solutions of the liquid phase. So just I am writing down some of the so if you take mixture of species, Fi of liquid is equal to xi gamma I pi set into phi I set, and the mixture of species for an ideal gas can be written as like vapor if you type okay. Now according to the Raoult's law, gamma I equal to 1 and m5 of liquid is equal to xi psi. Also we have seen Henry's law. Okay, now if you take it for a pure species, so if we take for pure species, Fi of liquid equal to psi, and for pure species, if for moderate pressure and ideal vapor, okay, psi. Okay, so these are some of the things. Now, okay, so just to summarize up what is an isotope and how to identify the isotopic compositions mixture. So this is I'm writing for the isotopic composition, how to identify. Now there is the calling criteria for stability of now what is this criteria actually? So this comes out to be t square then g by r is divided by the x1 square should be greater than 0, and this is at constant temperature pressure. Okay, so these are some of the things which has been covered during the entire week, and I don't want to go into the deep into and like in the various concepts, but it's just I'm laying on some of the top, some of the formulas and how to look at that gas. Okay, now what we'll do is that we'll see some of the things which has been explained during the week contents. So according to the ideal solutions and division from the ideal dilute solutions. So the first thing is known as the activity coefficients. Okay, activity coefficient equations. They are like similar for the non-ideal gases. We have equation of states. For non-ideal solutions, we have different activity coefficient equations. We known as marvelous 3 suffix, marvelous 2 suffix, Bose 3 suffix equations, and many more. So we'll just go through the equations finally. They have their own derivations and it can be derived, but only and unless if you know the basic concepts of why they have been used here. Okay, so similarly like for the non-ideal gases, we have various non-ideal equation of states. For non-ideal solutions, we derive from like positive derivation from the ideality or negative derivation from the ideality or the forms and isotopic mixture. We have like different components or the different equations which can be used in the for solving the problems, numerical problems. So the first one is known, what we are showing up here is directly the whole series of equations. So all these equations are shown in the final format. We have not derived from the critical. We have just taken from the reference books and I'm just showing up here. So the plus 3 suffix equation, there will be a 3-parameter equation which has been given by this one Z1 and Z2. Then in order to find out the activity. So the gamma 1 and gamma 2 are the activity coefficients of the component 1 and 2. And we have this equation, if you see Z1 and Z2 and Z1 and Z2 are none other the effective volume fraction that has been given to us of the separate components in the solution. Okay, So like I said, you don't have to mug up this equation, but unless and until in the final examination this is not given, then that might be a case you might have to remember this final format of this equation in order to solve the numericals. Okay, I'm just showing up what these equations are known about and how they can be used in the final examinations. Another one they have been using is called the Margulis 2 suffix or Margulis 3 suffix equations. So this one is the simplest one of the Margulis equation, in which if A is equal to B, so this equation is known as Margulis suffix equation. Okay, so if I take the equivalent mixture of A and B and it's say A equal to B, then Margulis equation can be taken as ln gamma 1 equal to AX1 square and ln gamma 2 is equal to ln gamma 1 is equal to AX2 square and ln gamma 2 is equal to AX1 square. But this only complies if A is equal to B. Otherwise, Margulis suffix equation can be written in the form of above that I have mentioned to you. Okay. Similarly, we have like Van Laar equation. Like we have seen Wolf's 3 suffix, Margulis 2 suffix, Margulis 3 suffix equation, and there is another form called Van Laar equation. So they have their own parameters and assumptions and the principles why this equation can be used and where they have to be used. But in the examination, with the in all the numericals, they will be saying, and sometimes they will ask you to solve it in these equations, or if they will be given no options, then you have to know on your own that okay, this is the concept that have been asked in the question, and this is the concept that can be related to these non-ideal equations like activity coefficient equations. Okay, so all these equations are related in order to find out the value of the activity coefficient, that is ultimately gamma 1 and gamma 2. So in all this equation you will see there is a gamma 1 and gamma 2, and the parameters A and B can be found out using this different equations. Okay, so just remember all these equations like Margulis 2 suffix, Margulis 3 suffix, Margulis Van Laar equation, Wolf's 3 suffix equation are there in order to find out the value of the activity coefficient parameter gamma 1 and gamma 2. Okay, similarly this is Wilson equation. Similarly we are going to find activity coefficient gamma 1 and gamma 2, and lambda 1 2 and lambda 2 1 are the two different parameters that have been used in this equation, and have been. So first you have to find out the value of lambda 1 2 and lambda 2 1. You have to put both of this value up here because you can see it's coming up here also. Okay, then you have to arrive at a final answer of gamma 1 and gamma 2, and then you can use this gamma 1 and gamma 2 to find out the value of the pressure or saturation, vapor pressure or anything, or viscosity or activity coefficients. Okay, and this is the last one, which is known as the non-random two liquid equations, NRTL. It is one of the famous equations in chemical engineering thermodynamics. Okay, similarly this is also equation used to find out the activity coefficients and activity coefficients. This is one of the things which is used to identify the activity coefficient model, and here we have, instead of gamma and gamma 2, we have two different parameters, G21 and G12, because they have similar to like Van Laar equation. We have been using these two parameters, and tau12 and tau21. Okay, so all these parameters that has been mentioned to is not just directly taken from some like references. They have their own specific meanings, and why they have been here is just you can go through the concept that has been discussed in the lecture notes. Okay, so now what we'll do, we'll directly jump on to solve some of the numericals quickly with the help of this the equations, like the activity coefficient models which we have gone through. Okay. So the first question which you are going to see states something like that. So the liquid A and B forms an isotopic mixture, okay, which contains a 46 mole percent of A at atmospheric pressure of 101.325 kilopascal and 345 Kelvin. So we will say, we will write down what is given. Temperature is 345 Kelvin. Pressure is 101.325 kilopascal. Okay, and we'll say let the two different liquids given A and B. So let A be component 1 and B be component 2. Now we have been given with the vapor pressure of A is 4.8 and B is this. Calculate the Van Laar constants. So there are Van Laar constants A and B. Okay, so I will show you what are the Van Laar constants. So if you see van der constants are known as A and B, so we have to find out these values, these two. But in order to find out the value of A and B, we need the value of active coefficient 1 and active coefficient of 2. So we'll try proceed. So first we'll find out gamma 1 is equal to P by P1 set. So the total pressure is 101.325 kilopascal. Your vapor pressure of 1 is 84.8. So if you solve this, it will come out 1.195. Similarly, gamma 2 is equal to P by vapor pressure of 2 is equal to 101.325 kilopascal divided by 78.2 kilopascal. So this comes out to 1.295. Okay, now we have been given x1 as 0.461 and x2 will be 1 minus 0.461, it comes out to 0.539. Okay, this is x1, this is x2. Now what we'll do is that we'll take the van der constant equation which we have shown to you earlier. Therefore van der constants A and B, so ln of gamma 1 1 plus x2 ln gamma 2 x1 ln gamma 1 whole square. We'll try to solve it out. We know that ln gamma 1 is 1.195, 1 plus x2 is 0.539, ln of gamma 2 1.295 divided by x1 is 0.461 into ln of 1.195. So just if you solve this entire equation and find out the value of it, it comes out to be 1.295. Okay. Similarly, we will find out the van der constant B, that is ln gamma 2 1 plus x1 ln gamma 1 upon x2 ln gamma 2 whole square. So ln gamma 2 is 1.295, 1 plus x1 is 0.461 ln of 1.195 divided by x2 is 0.539 into ln of gamma 2 is 1.295. So this comes out to be 0.653. So these are the two values of A and B, which are the van der constants. Okay, so this is just like a simple equation which can be asked in the final examinations for 2 marks. Similarly, there are different constants like Wilson constants A and B, and non-NRTL equations like non-2 liquid constants A and B. So this is just I solved it for the simplest one, which is known as the van der constants, and we have been able to identify the value of A and B. Now they say to find out if they give the value of A and B and they said you need to find out the value of gamma 1 and gamma 2, you can use the equation of van der constants for the active coefficient models that can find out the value of active coefficients for component 1 and component 2 in the reverse manner. Okay. So this is one kind of the question that I wanted to discuss, and I'll just explain the form of printed format here for you guys, because sometimes my handwriting will not be good, it's not a proper way, so that's why I'm putting the printed format also here for you guys. So what I've done is that we have taken material as component 1 and component as material 2. So we have calculated gamma 1 and gamma 2 activity coefficients, and now what we did is that we have substituted the value of so x1 is given to us at 46.1%, so x1 plus x2 equal to 1, x2 equal to 1 minus x1. Okay, and then we are able to find out this value. Now we use these two equations, which is known as the van der constants A and B, and we are able to find out the values of A and B. So these are the final answers. So this is A, this is B, and these are the final answers. Okay, we'll move up to next question. So we have been given an isotope of ethanol benzene system. So the ethanol and benzene forms an isotope, and we have been asked has a composition. So the ethanol benzene system has a composition of 48% of mole of ethanol with a boiling point of 341.4 Kelvin at 101.3 kilopascal. At this temperature, the vapor pressure of benzene is given is 68.9 kilopascal and the vapor pressure of ethanol is 67.4 kilopascal. What are the activity coefficients in a solution containing 10% alcohol? Okay, so at one point, go to the question. Even in the final examinations, it looks like a big question, like 4-line question. But do not get like tricked with the type of the questions they will be asking. But read it thoroughly, slowly, and write it down line to line. If you're reading the first line, please write it down what is mentioned in the first question. Okay, then go to the second question and try to identify what is mentioned and write it down the given data. So the first and the foremost thing in the final examinations that I do by myself is that I will go through line by line. I read each and everything. Whatever data they have mentioned, it doesn't matter if I'm not able to understand at one point. But what I will do is that I will try to write it down one by one. So if given data is, suppose if you read the first line, so they have a composition of 44.81% of ethanol. So the remaining will be benzene because it forms an azeotropic mixture. Okay, and similarly like the temperature, pressure, everything, just write it down in the form of a given data. Okay, so what we'll do, we'll try to solve it out. So you can assume on your own if you want to take, it's your wish, if you want to take ethanol as component 1 or benzene as a component 2, you can take on your own wish. Just be remember there has to be uniformity while solving the numerical. Okay. Okay, so we have taken, and what we'll do, we'll find out the value of activity coefficient of first component. So total pressure is going to is 101.325, and the saturation vapor pressure of benzene and vapor pressure of ethanol is given to us. So since we have taken benzene as component 1, it will be 68.9. Similarly, gamma 2 is equal to P by P2S is equal to 101.3 and 67.4. Okay, so this turns out to be 1.47 and 1.50. Okay, now we have been given the ethanol. So ethanol is component 2, so x2 equal to 1448, x1 equal to 1 minus x1 equal to 1 minus 0.448. Therefore x1 comes out to be 0.552. Okay, so this is one of the things. Now we have to identify what are the activity coefficients in a solution. So what we will do, we will use a Van Laer equation for determining the Van Laer constants. Since nothing has been given, we will use the simplest one, which is known as the Van Laer equation. So we'll first find out the Van Laer constants equal to ln gamma 1 plus x2 by x1 ln of gamma 2 ln of gamma 1 whole square. Similarly, will be equal to ln of gamma 2 1 plus x1 ln of gamma 1 x2 ln of gamma 2 whole square. Okay, so this comes out to be ln gamma 1 is 1.47, 1 plus x2 is 0.44 into ln of 1.50 whole square. X1 is 0.55, ln of 1.47. Similarly, put all the values here. Ln of gamma 2 is 1.50 1 plus 0.55 ln of 1.47. So after finding this out, you will be able to find out the value of A and B, which comes out to be 1.33 and 1.91. Now, for a solution containing 10% of the alcohols, and that has been given to us. For solution %10 of the alcohol, therefore ethanol is taken as a component 2. So x1 will be x2 is ethanol, that is alcohol. The 10% is 0.1 and the remaining will be 0.9, that is benzene. Now calculating the activity coefficients using this, therefore ln of gamma 1 equal to ax2 square divided by a by b x1 plus x2 का whole square. Similarly ln of gamma 2 is equal to b x1 square b by a x2 plus x1 का whole square. So if you put all the values, this comes out to be 0.0025 and 1.421. Okay, so what we did is that we have used the Van Laar equation, the activity coefficient model, and you've taken ethanol as a component 1 and benzene as a component ethanol as a component 2 and benzene as a component 1. Like I said, you can choose on your own. It's not a matter of concept, but the only thing is that you have to maintain the same uniformity during the entire numerical, because if you switch in between that, like benzene as a component to ethanol component, it will be around point with the answer which you are arriving. Okay, so first what we did, we have taken the pressure temperature. So this is the temperature is 4144 Kelvin and pressure is given as 1 atmosphere, that is 101.325 kilopascal. We have found out the value of the activity coefficients gamma 1 and gamma 2, and we have used these equations in order to find out the Van Laar constants. So we have found out the Van Laar constants A and B, and from that what has been asked to us in the question is that what are the activity coefficients in the solution containing 10% of the alcohol. So since we have taken ethanol as a component 2, so the component 2 is ethanol, so the 10% means 0.1 and the remaining is benzene, that is 90% is 0.9. And from this equation we have found out the value of okay. So what has been asked, what is the activity coefficient? So we have found out the value of gamma 1 and gamma 2 through this value. So this is gamma 1, this is gamma 2, and these two are the answers for the solution containing 10% of the alcohol. Okay. So this is how this non-ideal solutions and the activity coefficients model can be used to identify the value of gamma 1 and gamma 2, that is activity coefficients. If nothing is given, you can assume any equations and solve it. But please remember, try to maintain the uniformity to the entire solution of the numerical. Okay. So this is the another like the printed form, because sometimes, like I said in the previous classes, I think some of the students are not able to understand my handwriting because I'm writing too fast. Frankly, it's like it's not proper. So what I'm doing from now onwards is that I'm typing it down and just keeping the same things in the printed format. So it's easier for some of the guys who are not able to understand my handwriting also. Okay, so like I said, I've been taking component 1 as benzene and alcohol as component 2. We found out the value of gamma 1 and gamma 2, and from like the mole fraction is given to us as a component of 44.8% of ethanol. So since x1 plus x2 equal to 1, we have been given x2, we can find out x1 is 1 minus 0.448 is 0.552. Okay, and what we did is that we used Van Laar equation to ultimately find out the value. So this is A, this is B. There are some of the Van Laar constants, and from this Van Laar constant we will be able to identify the activity quotient, because they have been told us to find out the activity in the solution containing 10% of the alcohol. Now since we have taken alcohol, that is ethanol, as component 2, so if we say 10%, so x2 will be 0.1, the remaining is x1 is 0.9, that is benzene. And from this equation, that is the Van equation, we are able to find out the value of gamma 1 and gamma 2, which is printed here. So these are the final answer. Okay, like I said, I have used Van equation here, but you can also use different equations like the marvelous 2 suffix or marvelous 3 suffix and try to solve it. But they all have like the variation in the final answer. These variations might be because of the assumptions and the principles they have been taken by deriving at these equations. So please go through the assumptions and the principles that has been considered while arriving at these particular equations. Okay, so it has already been discussed in the classes. Plus, please go through the lecture notes and everything and the reference books. You will be able to find out what the assumptions and the principle for these cases. Okay, I will move up to the next question. So here I will first go through the question what has been given to us. Okay, so the temperature and pressure is given. So the temperature of 318 Kelvin and a pressure of 24.4 kilopascal, the composition of the system containing ethanol as component 1. So now if they mention 1 as ethanol, we have to take ethanol as component 1. Although in some of the questions they will not be mentioning what is component 1 and component 2, but here they have clearly mentioned that take ethanol as component 1 and toluene as component 2. And they have given an equilibrium compositions of x1 and y1. So x1 is 0.3 and y1 is 0.634. The saturation pressure is given temperature for the pure components. Now we have to identify the saturation vapor pressure, okay, for the pure components respectively. So what they have been asked is to calculate the liquid phase activity coefficients and the value of Gibbs free energy, excess Gibbs free energy by RT for the liquid phase. Okay, so what we'll do is that we know that yi into P is equal to xi gamma I pi z. So this is the equation that I have already mentioned during starting of the class. Therefore, so liquid phase activity coefficient, that is gamma I. So we'll take gamma 1 equal to y1 into P divided by x1 equal to P1 set, and similarly gamma 2 equal to y2 into P x2 into P2 set. So y1 is 0.634, total pressure is 24.4, x1 is given to us as 0.3 into saturation vapor pressure of. So I forgot to mention here the saturation vapor pressure. So the pure component I will mention as is, I forgot to mention in the question, but it's like P1 saturation is 23.06 and P2 is 10.05. So these two are already there in the question. Okay, so there's a printing mistake here, but it's already mentioned the saturation vapor pressure. Okay, so just don't worry about that. So we haven't taken this, and y2 will be similarly 0.366 into 24.4 divided by x2 will be x1 is 0.6, x1 is 0.3, so x2 will be 1 minus 0.8 is 0.7 into P2 set 10.05. So if you solve this, you will find out the value of gamma 1 and gamma 2, and that is 2.23 and 1.26. Now they have been told us to find out the value of G by RT. Okay, so what we'll do, that is the P question that been asked, the excess Gibbs free energy. We'll see the excess energy. Is related to the activity coefficient by the following equation. Therefore, we have been asked to identify the excess Gibbs free energy Okay. So this equation we have already seen, that is known as one of the well-known equation, thermodynamic consistency. We have seen in the past time and how to identify that equation also. Okay. So this term we have to identify. Therefore, G by RT x1 is going to as 0.3. Activity coefficient of gamma 1 is 2.23 from previous solution, and x2 is 1 minus x1, that is 1 minus 0.3 is 0.7. ln of gamma 2 is 1.26. So this comes out to be 0.4084. So this is the final answer. Okay. So this is the simplest one. Just need to identify like what to do and what not to do, and which equations you have to use. Okay. So in this today live interactive session, this is what so this is in the printed form, just for you guys for the quick understanding. We have first found out the value of gamma 1 and gamma 2, and then what we have done, we have used this gamma 1 gamma 2 values in order to find out the value of excess diffusion energy, that is known as thermodynamic consistency equation. Xn and gamma 1 and Xn and gamma 2, if the binary mixture components are there. Okay, so the final answer is this. So this is what I have for today. I have a lot more questions to solve, but the thing is, we want to start it like just not directly use just NRDL equations and just complex equations within the one go. So what I did today is that we have gone through some of the non-ideal solutions. What is non-ideal solutions? We have seen what are isotopes, maximum boiling isotope, minimum boiling isotope, and we have gone through some of the concepts related to the different activity coefficient models. The first one was Wilson equation. The second one was, what do you say, uh, Margulis 2 suffix, Margulis 3 suffix, and then you went on to see what is Wilson equation, Van equation, their Van constants and the various constants of the various equation. Then you went on to last one, which is known as NRTL, that is non-random two liquid equations. And we have started beginning with some of the numericals and how to relate this non-ideal solutions with the numericals, and how to identify the various parameters using the this activity coefficient models, that is gamma 1, gamma 2, and even in some of the questions they will ask what are the various activity models. Then if you see this equation, you can see, okay, these are some of the activity based coefficient models which can be used to identify the value of the activity coefficients, that is gamma 1 and gamma 2, which are there in the equations related to the non-ideal solutions. Okay. So this thing you have to remember, because sometimes they will ask just to check your mindset, if you know the basic concepts, what are these equations have been used for. So they will list like in the MCQs A, B, C, D, out of all these options mentioned below, which are been used as for the activity coefficient models and which has some particular value. They will also ask you to identify what are the constants values A and B corresponds to, if they give 4 options. So if you must know all the things, it will be easier for you guys to identify the parameters and all the things within one go. Okay, so this is what I have for today. We'll meet up next week at the same time from 3 o'clock for the week 10 live interactive session, and the next week we will be able to solve much of more of the numericals uh, like related to more to Wilson, Margulis 2 suffix, Margulis 3 suffix, and NRTL equation also. So today we have covered related to the simplest one, that is so Margulis 2 suffix and 3 suffix are also the simplest one, but we have seen somewhat related to Van constants and the Van activity coefficient model, and you solve someone related to the isotopic compositions also. Okay. So if any one of you have any questions related to the concepts or the numericals and the assignment or tutorial problems that has been displayed on the NPTEL swim board, please do let me know. Also, if you face any issues related to anything related to solving some of the numericals out of the context from the uh, lecture contents, please do not hesitate to let me ask in this live interactive sessions. I will be able to help you out very firmly. Okay, so till then, it's good. Please be prepared for the final examinations. It's going to be in just within a 1 month or 1.5 months of gap, and we have been left with like 3 live interactive sessions more, that is 10th, 11th, and 12th, and we'll try to cover up wind up as soon as possible. And then in the last live interactive session, what we'll do is that once we wind up the last interactive session, we will have like a similar like more than half an hour addition to that in the 12 week 12. Like we cover up from the basic concepts starting from week 1 to week 12 and try to summarize within the half an hour. So all the contents will be summarized, and we'll see what are the important things which you have to remember, you have to go through for the final examinations. Okay. Till then, we'll meet till next week. in the week 10, the Saturday from 3 o'clock. Okay, till then, thank you for joining this live and text session. We'll meet next week. Thank you guys. Thank you.